Hello, we are going to spend this video determining the empirical formula if we're given moles, masses, or percent compositions. So we know that compounds have a fixed ratio of elements within that compound. So this follows the law of definite proportions. So we can use that to use data to figure out the empirical formula of various compounds. The empirical formula is the lowest whole number ratio of atoms of the elements within the compound. So for example, if we have B2H6, that would be the molecular formula. So that might be how that molecule actually exists. Its empirical formula is going to be taking that and dividing all the coefficients by the greatest common factor. So I can divide those both by 2. So its empirical formula would be BH3. Okay, if I were to look at, like, say, glucose, which you guys are familiar with from biology, so that would be the actual molecular formula. That's how those atoms are actually bonded, in the compound. If I look at the empirical formula, in this case, I can divide all the subscripts by 6. So its ratio would be CH2O, okay, or it's in a 1 to 2 to 1 ratio. Okay, so that's just kind of an introduction. You need to know the definition of an empirical formula. You need to know how to find the empirical formula from the molecular formula. So now we're going to get into, well, how do we actually use data to come up with our empirical formula, or this lowest ratio within a compound? So the first way we're going to look at it is just looking at the moles that were given to us. So in this case, we have potassium, carbon, and oxygen. Now you can think of, if I were to write this out in this format, with our potassium, our moles of carbon, and our moles of oxygen. Okay, you would never see that formula written like that with those without whole numbers in for the subscripts. So a way to get them into whole numbers is to simply divide them all by the smallest. So since carbon's moles is the smallest, I'm going to divide them all by 0.052. That will allow carbon to be set to 1, and then we'll check all the other ones once we do this. So when we go and do this, then we'll see that K, 0.104 divided by 0.052 gives us exactly a 2. Carbon is going to be that 1, which we would end up dropping, and then oxygen, when you divide those two, will give you a 3. So that mole data will end up giving us then this potassium carbonate formula. All right, we're going to use that strategy, but we're going to kind of add on an extra piece here. Most of the time we're dealing with, say, grams. So we've been able to analyze a compound. Say you've been able to figure out how many grams of, in this case, tin and fluorine we have. What's the empirical formula? Because again, the ratio between this tin and fluorine is going to allow us to determine that. So the first thing we want to take care of, though, is we want to get this into moles. So we're going to use the relationship between moles and mass, which is dealing with the molar mass of each element. I would say get right off into the habit of keeping everything very organized, because we're going to keep adding to this and building on it. So the more organized you keep it, the better. All right, so with tin, I have 5.28 grams. And with fluorine, there was 3.37 grams. Okay, I'm going to do each and calculate the moles, and I'm just using values off of my periodic table. So for tin, the molar mass is 118.71 grams, and this is 1 mole. Okay, when I divide those two, I'm going to keep my 3 sig figs that I was given to start with, and that gives me 0.0445 moles. So this is our moles of tin. Then I'm going to deal with fluorine. So fluorine's molar mass is 19.00. That's 1 mole of it. So when you divide those two, you're going to get 0.177, and this is your moles of fluorine. Okay. Now that we have moles of the two based off of their grams, now it's going to be just like the first example that we just went through, where now I just need to get them into a whole number ratio. So with this one, I'm going to divide them by the smallest. So I'm going to divide them by 0.0445. That will set tin equal to 1. 445 here. When you do that on your calculator, see if you can see that a little bit in there. You're going to get this 3.97752 number. That's close enough that it is acceptable for us to round that to 4. So we can round that to a whole number of 4. Okay, now that they're in whole numbers, I can write this as SNF4. So that would be the empirical formula based on that data. All right, the next example here is usually how we find these questions. This is going to be what is the empirical formula of a compound, having a composition where we have the percentages of each element given to us. Okay, and this is usually how we would probably analyze in the lab in terms of figuring out how much of each element you have. So in the next piece here, we're going to simply assume that we have 100 grams of the compound. Okay, what that allows us to do is basically bring us right back to where we were working in the last one, where we're going to have our two elements. Okay, I'm going to say if I had 38.76% of 100 grams, that would be 38.76 grams. And then I'm going to do the same thing with oxygen. So I'm just simply going to assume that I have 100 grams of this compound, which allows me to take my percentages and just put them into grams. Then from there, it's the same set of steps as we were just working on. Okay, I'm going to take chlorine and using its molar mass. Okay, I'm going to divide those two and I get 1.093 moles of Cl. Then I'm going to do the same thing for oxygen using its molar mass of 16.0 grams. Which is equivalent to 1 mole of oxygen, and that gives me, in this case, 3.828, and that's my mole of oxygen. So in this one, you are going to see a little bit different than the last one, because when we go and divide by the smallest, okay, chlorine is 1, but when we divide oxygen by the 1.093, okay, you're going to see that this gets very close to 3.5, and that we actually have to write down as 3.5. Okay, so we're still not in whole numbers. Okay, so we have to get these into whole numbers. So in order to do that, I'm going to multiply 3.5 by 2. Whatever I do to 1, I have to do to any of my other subscripts here. So I'm going to have to multiply this also by my 2. So when I do that, I get a 2 moles for chlorine for every 7 moles of oxygen, which then is going to give me my formula. So Cl2O7, that would be my empirical formula based on this data. This little flowchart at the bottom just kind of walks you through the steps that we just went through. We took their mass percents, we assumed a 100-gram sample, we got grams. Using molar masses, we got to moles, and then we calculated that mole ratio within the compound and got our empirical formula. Okay, so definitely take the time to go through this and practice it, and then we're going to build on it in our next lesson when we use this to then figure out our molecular formula.